Hey guys, Mr. L coming back at you with another video. And in this video, we're going to talk about entropy, or the randomness in the universe. We're going to talk about spontaneous and non-spontaneous processes, reversible versus irreversible processes, and the second law of thermodynamics. So let's get into this video. The first thing we're going to talk about is a reminder of all the different heat things we've covered in previous videos. So we covered enthalpy, which is delta H, or the change in heat value at constant pressure. And we saw that heat and energy can't be created or destroyed. That's based off of the law of conservation of mass. And that also led us to the first law of thermodynamics. Energy can't be created or destroyed, but it can be exchanged between the system, or the particles that we're interested in studying, and the surroundings, which is the rest of the universe. So heat can go in and out of that system as it wishes. The other thing we're going to start talking about in this video is entropy. Entropy is symbolized using a capital S, or delta S, for change in entropy. And this is the measure of randomness a system has, or how many particles that are all spread out, or how many different bonds they have. There's going to be all different types of randomness that you can come across. So both of these are going to be important, the heat value and the randomness value, when we go to see whether something will occur, whether it's spontaneous or it won't occur. It's non-spontaneous under these different sets of conditions. And the symbol that we would use for this is capital G, or delta G, which is Gibbs energy. So now what we're going to talk about is the idea of a spontaneous process. So what spontaneous means in chemistry class is that it's going to happen without any outside influence. So an analogy I like to use for this is if I had this box here and I were to drop it, it's spontaneously going to go towards the gravitational source. So as you can see, the box fell to the floor without any outside influence. I didn't push it down, it fell due to the gravitational field of the Earth, and it wants to go towards the center of that gravitational field. So this occurred spontaneously. Then we can ask ourselves, what's the likelihood that the box is going to fly up into my hand like a Jedi? The answer is it's not. The value is going to be 0. It is not probable at all. So whatever is spontaneous in one direction is non-spontaneous in the opposite direction. In order for the box to get up to this elevation, I'm going to need to do work to bend down and pick the box up to this elevation. So this is non-spontaneous in the opposite direction. Another analogy that we can think about is if we've got gases and we've got a flask. If we've got gases that are in flask A and we've got no gas in flask B, and we open the valve, the likelihood that A will spread into flask B is very likely due to diffusion. But there is no likelihood that all the gas, once it's in flask B and equally separated, that it's going to all cram back into flask A and shut the door behind itself. That is not spontaneous in this direction. So whatever is spontaneous in one direction is non-spontaneous in the opposite direction. The other thing we need to keep in mind about this, though, is there may be some threshold value. So if we have something like ice here, if we put the ice in a 10 degrees Celsius room, it will spontaneously melt because it's above the melting temperature. If we put that same ice in a room that's at negative 10 degrees Celsius, nothing is going to happen because we haven't hit the temperature threshold value in order for melting to occur. So there may be some threshold that you need to overcome before the process then becomes spontaneous. So now we can briefly talk about reversible versus irreversible processes. So if we have something like heat exchange between an object and the surroundings, the heat can go from the object to the surroundings and vice versa. Heat could go from the surroundings and heat up the object. This is a reversible process, so heat transfer is reversible. It doesn't take any outside work for this heat to flow from one area to the next. But if we had another example like a piston with some gases in half of the piston, and we open this door, the gases are going to diffuse and fill up the whole piston. It's not going to all cram back into that half of the piston and let the door slide down behind itself. That's not going to happen. In order for you to put those gases in that same amount of volume that it began with, you're going to need to do work to compress it to that size in order to shut the door. So this is an irreversible process. So now we can start talking about entropy, or the amount of randomness, as a numerical value. So just like enthalpy delta H, entropy delta S is also a state function. So it's irrelevant of the pathway that it took to get there. As long as you know the initial value and the final value, we can calculate the change in randomness. So the other way that we can do this is delta S is equal to the reversible heat value, so Q reverse, over temperature. And this is important. We got to remember that our temperature is going to be an absolute temperature, and this is going to be done at a constant temperature. So we're going to need a constant temperature in the unit Kelvin. And we're eventually going to get to the third law of thermodynamics, which is absolute zero or 0 Kelvin. So this is why we need to use this. The units on our change in entropy are generally joule per mole Kelvin. So the last thing we're going to talk about is the idea of the second law of thermodynamics. The second law of thermodynamics states that the entropy or randomness of the universe is going to be increasing with any spontaneous process. So anything that happens spontaneously is going to result in the universe getting more and more random. So we can see that delta S of the universe is equal to the system plus surroundings, and that could be equal to 0 for a reversible process. So if heat is being exchanged, we've got a reversible process, and the entropy of the universe is equal to 0. For a spontaneous irreversible process though, we've got system plus surroundings is going to be greater than 0. So entropy or randomness of the universe is always getting more and more random. We can put in work to organize the system, such as homeostasis, like in organisms. We've got cells that are constantly cleaning. We're taking in resources and putting out different products into the environment. And we're trying to maintain this homeostasis, but eventually our cells are going to die out and we will perish. And when we perish, all the particles are going to decompose and go back into the earth, and everything's going to get more and more random. So you can put in work. Another less morbid analogy might be like your room. You get home, you clean your room, but then after time, dust is going to settle, your clothes might be on the floor, and everything is going to get dirtier and more random until you put in work and organize the system. So there it is, you guys. There's a video on spontaneous processes, reversible and irreversible processes, entropy, and the second law of thermodynamics. So if you enjoyed this video, if you found it useful, smash the like button, send it to your favorite band, send it to your favorite Disney creature, and we'll see you in the next video.